Okay, so today we're going to learn about our last type of t-test, a two samples or independent samples t-test. Okay, we saw this slide before, and just as a reminder, comparing two groups like a treatment and control is very common. We've seen the paired sample, such as a before and after. Now we want to see what it would mean if the two groups were separate from each other and independent from each other. And looking at this graphic again, so you can see every square here is an experimental unit, and red might be your control group and yellow are your treatment group. And so they are not related in any way per se. I know we're sampling from quote unquote the same population, but there's no natural pairing. They should be independent from each other. So let's look at what our null hypothesis would look like under a two samples t-test or two independent samples t-test. Okay, so I pulled up the Salk vaccine example for the null hypothesis. So you can see that in the Salk vaccine we had a two sample design going on there. We had a group of randomly sampled children that were given a placebo shot and a group of randomly sampled children that were given the vaccine, and then we measured the mean rate of infection between those two groups. Under the null, and it would be that they're equal, or we can say the mean of the vaccine minus the mean of control equals 0. So mathematically that's the same. The alternative here then is there is no difference. Okay, so I'm bringing this slide up again just to remind you we're still following these basic steps when we're doing our statistical null hypothesis testing procedure for all the t-tests that we're doing, and we will keep our alpha level at 0.05. So for any t-test, we had this sort of general idea, the statistic minus the hypothesis value over the standard error of the statistic, and that was signal over the noise. So I've added the two independent samples t-test to this slide. And you might say, hey, where's the hypothesized value? Well, it's not really written here because generally speaking, and unless it was different from, we would expect that to be 0. So it would be the mean of one group minus the mean of the other minus 0 here. And we get a different type of standard error, and we'll discuss that more. There are assumptions, just like we saw in the one sample and the paired: independence of observations, random sampling, normal distribution of the data. We do need to add something though. In a case of a two samples, because they're two independent samples, we would like to have equal variances here. It helps us know that the probability value that we get with our test statistic is accurate. So when we test for equal variances or homogeneity of variances, when we look at your data, one of the things you can do is look at your standard deviations. And they should be within 3 times of each other. What that means is, say my control standard deviation is 1.2 and my treatment standard deviation is 2.3. If I took that 1.2 and multiplied it by 3, it overlaps the 2.3. As a matter of fact, goes beyond that 3. So they'll probably be the same or equal in that case. But that's an eyeball way. So sometimes when you're looking at your data, if you see big differences in those standard deviations, you might be thinking, uh-oh. So we're still going to run a specific test for this. We're going to use a hypothesis test that is a flight check, just like we did with the Anderson-Darling test for normality. It's called the F test, and it's a ratio test. We take the variance of one group over the variance of the other, and if they're equal, that ratio will equal 1. Okay, here absent and present just doesn't mean anything. That could be control and treatment. So what we're looking for is to see what that F ratio gives. If it's close to 1, then we'll have a p-value above 0.05, and that means, yay, we have equal variances. this is the distribution that it's based on. We usually think of this as a one-tailed test, because as a rule we'll put the larger sample variance in the numerator and the smaller one on the bottom. So we'll be looking at the probability associated with that ratio and that value, and to the right, larger than that. There's another similar one, and we'll see this on Minitab. It's called Levene's. Okay, the F-test is good, and they're both based on these ratios of the variances. The F-test has the most power, but if your data is not really normally distributed, it can be problematic, which is hard to sometimes see with small data sets. So we can also use Levene's test. It can work with more than 2 groups, where this F-test only works with 2 groups, like a control and treatment. So we can use Levene's when we start going into the ANOVAs. And they usually agree, but if you have really small sample sizes and you're not sure about normality, use Levene's. Okay, so let me show you an example, living versus dead horned lizards. Okay, so horned lizards have these spikes along the back of their skulls, and it's thought to be an anti-predator adaptation because shrikes, which are a type of bird and are a predator of these lizards, come and pick them up. So you can see that in that bottom picture. And then they impale those little lizards on thorns, and then they eat them. So what they think might be happening is that the longer your horns are as a lizard, the more likely you are to escape predation. So we think that the impaled skulls, the ones they find that have been eaten, probably have shorter spikes than the living lizards. So notice, this is an observational study. We're not tweaking anything. Here's the data. Okay, let's see what we got here. The killed, the ones that were impaled, had a horn length mean of 21.99 with a standard deviation of 2.71. The living lizards had a horn length of 24.28 with a standard deviation of 2.63. Notice we don't have even sample size here. Sometimes that's not what we're aiming for. But usually our t-tests are pretty robust to unbalanced design, but we prefer balanced design. But this is what we found out in the field. Okay, so right now we're saying, hey, if I'm just looking at those means, the mean in the living looks bigger than the ones that have died. My standard deviations look almost equal, so that is good. And so now I want to know if the difference between these is likely to have occurred by chance, just random sampling error. All right, null hypothesis again. Okay, so in this case, the mean of the horn length for the living would equal the mean of the horn length for the dead. Okay, positive and negative differences should occur equally frequently around 0. And small differences between means would be common, and increasingly big differences would be increasingly less common. So we'll see that in the way that test statistic is calculated, the bigger difference you have between means, the more likely you're going to have a stronger signal to the noise. Okay, under the null, these 2 samples come from one population. Now, it sounds sort of silly because you think, well, they're all the same species. Of course they're one population. But that really is what we're saying under the null hypothesis, that there is no difference, so they come from one main population sampling distribution. And then the alternative is really saying, hey, are these really representative of 2 different distributions from 2 different populations, as it were? All right, well, before I do anything else, I've looked at my data. I've seen that the living ones seem to have longer horn length than the dead ones. And so I'm going to make sure that my data is normal. Of course, in experimental design, I've know I have independence of observations and random sampling because we do good experimental design. My normality here, I'm saying check. Now you may notice that the p-values with these Anderson-Darlings are low, especially for the one group. That one group is the living. The zero group is the dead. But my sample size is so large, I'm ignoring it because the t-test, the two-sample t-test, is robust to deviations of normality when my sample size is really large. So I'm ignoring it. If I didn't have large sample size, I would not ignore this here. And then I checked for my HOV, my equal variances. Notice I was worried about normality here, so I didn't use the F-test. I used Levene's, and I have a high p-value, so check I have equal variances. So we need to calculate the test statistic, and here it is again, and I'm circling this standard error for the mean difference. This is a different type of standard error than we've seen before. So it is calculated as a pooled sort of idea, and here's some calculations. You're not going to really need to remember these calculations. Just know that it's weighted by the sample size and or degrees of freedom if you really start to unpack that. And it's based on the pooled sample variance. And of course, then we take the square root of that for the standard error of the difference. So a weighted average. You'll see sometimes where different calculations for this, but basically they're all the same. What I want you to know is it is calculated a little bit differently than we've seen other standard errors because it's not standard error in just one mean. Okay, let's put in our data. So there's my difference between the means. There's my pooled variance. There's my standard error for the difference between means. And I put my difference over my standard error for the difference between means. And I get a test statistic of 4.35. So this means that there are 4.35 standard errors between one mean and the other. All right, what are we going to do? We're going to go to our theoretical sampling distribution. We need to know the degrees of freedom. The way we calculated degrees of freedom for a two-sample t-test is we take the sample size of one group plus the sample size of the other group minus 2. Why is it minus 2? Because what we're really saying is we're adding up the degrees of freedom from both samples. So n minus 1 for the living plus n minus 1 for the dead. So it comes out the same way mathematically, just adding up the two sample sizes minus 2. And here our degrees of freedom is 182. We find the critical value on our t-table at degrees of freedom of 182 and where we set our alpha at 0.05, and we find that it is plus or minus 1.97. So our t that we got in this experiment is way higher than that, and we have a low p-value below 0.05. So high t, low p, we're going to be rejecting our null. And we have another piece of information, the confidence interval for the difference, which use that pooled standard error. And now we see that under the null, right, the difference between those would be 0. If this confidence interval for the difference contained 0, we are going to have two groups that are significantly different. But this one doesn't cross 0. And so consistent with what we got with our test statistic and p-value, this tells, because it doesn't cross that null value of 0, then we have significant differences between the two groups. Also notice that we have a positive, okay, which means that y1 was larger than y2. And so that difference between means, 2.29. So those living shrikes had larger longer horns. So it's going in this direction that they are longer. So remember when I was talking about effect size, even if I had a non-significant P, I might look at this confidence interval, see which way it's going here. So since P is less than 0.05, our T is in the rejection region, our confidence interval didn't overlap 0 for the difference between means, so we're going to reject our null, and we look at those means in the direction of our confidence interval for the difference, and we can see that the living had significantly longer horns than the dead ones. So I put here the difference was 2.29 millimeters with a moderate effect size. Actually, that's pretty good, but depends on what field you're in, but a pretty good effect size. Now, effect size, we've talked about using confidence intervals for that, but there's some other common calculation we could do. So here's my commercial, is calculating effect size. This can be important to present in your data analyses, and the reason is that effect size can be used to tell not only did you get a significant difference, or not only did you not get a significant difference, but how much of an effect was there difference between these means. And so these are all the Cohen's, are called Cohen's d for effect size, and there's some rules of thumb. 0.1 is small, 0.5 is moderate, effect size of 1 or more is large, and of course this depends on the field you're in, but this is a good rule of thumb. And it can help other people who are following up with similar experiments. If you want to do meta-analyses, which we're not really going to get into here, but if you want to combine data from multiple experiments, effect size can be very important to have in your data analysis, so someone else could look at that and combine it with another study. Okay, the other thing I want to mention is not making indirect comparisons. So in your book, there's this thing that, hey, if we have some null value, why don't we just compare every sample to a null value, and then we can indirectly compare those two. So this is an example of baby pictures to 3 possible mothers or 3 possible fathers. If you're guessing, you're going to be right a third of the time. And so for people looking at the mother's pictures, guessing the right mother for the baby, for the baby picture, can guess the right mother, and it overlaps the null. But in the fathers, it does not overlap the null, so we say it's not different. But that does not mean that there's a difference in being able to tell the difference between identifying mothers and fathers as a direct comparison. We could not do it like this, because we don't have transitivity, okay? Remember, if A equals B and B equals C, then A equals C. Well, that doesn't happen here because we're talking about estimates and there's uncertainty. So we can't apply that kind of mathematical logic. So, example here, we are confident group 1 doesn't overlap some line, and that might be a null. But we are confident that about group 2, but we certainly wouldn't say then that the group 1 is different from group 2. We need to do like a 2-sample t-test and directly compare the two. So some people will say they interpret degrees of overlap in confidence intervals, and we need to be a little bit careful. There's one situation we can be kind of sure of, and 2 more we're not really sure. Here's what we have. In A, if your 2 95% confidence intervals around your means for the 2 groups do not overlap, you're going to get a high a high T test statistic and a low P. All that tells you reject the null. In B, generally you're not going to have significant difference. Generally, I say it. Because in this case, group 2's 95% confidence interval overlaps the mean of group 1. So whenever you have one or more of the confidence intervals overlapping the other group's means, you're most likely to you're not going to be rejecting your null. You're going to get a low T and a high P. It's here in C, we're not really sure. The confidence intervals overlap, but not to their means, so it could go either way. So why is this? It's because the confidence intervals for the difference in means is calculated differently than the confidence interval around the means. Okay, there's some math involved here. I don't want you to worry about that too much. I think, I want you to be able to look at confidence intervals and get an idea of what you think might be happening. So if they're not overlapping, the two groups are going to be significantly different. If the 95% confidence intervals in either group overlap the mean of the other group, likely not going to be different. It's when the confidence intervals overlap, but not to the point of their means, that we're not sure. And that's it for 2-sample t-tests.